How to design multi-branch wise sales forecasting in AI, ML, and deep learning by designing neural network in Python program. Pradeep K. Suri. Author and researcher. Designing a multi-branch sales forecasting system using AI, ML, and deep learning involves several steps. Here's a high-level overview of the process, including creating a neural network in a Python program. 1. Data collection and pre-processing. Gather historical sales data for each branch, including relevant features such as time, location, promotions, and more. Clean and pre-process the data, handling missing values and outliers and normalizing numerical features. 2. Feature engineering. Create meaningful features that can help the model capture patterns in the data. This might involve generating time-based features, aggregating data, or encoding categorical variables. 3. Data splitting. Split the dataset into training, validation, and test sets. The training set is used to train the model, the validation set helps tune hyperparameters, and the test set evaluates the final model's performance. 4. Model selection. Choose a suitable model architecture. In this case, a neural network is a good choice due to its ability to capture complex relationships in data. 5. Neural network architecture. Design a neural network architecture that suits your problem. For a sales forecasting problem, a common architecture could be a recurrent neural network, RNN, or a long short-term memory, LSTM, network. You can also experiment with more advanced architectures like a combination of CNN and LSTM or transformers. 6. Model design and implementation. Use a deep learning framework like TensorFlow or PyTorch to design and implement the chosen neural network architecture. You'll define the layers, activation functions, dropout, and other components. 7. Training. Train the neural network using the training dataset. Monitor its performance on the validation set to avoid overfitting. You can use metrics like mean absolute error, MAE, or root mean squared error, RMSE, for evaluation. 8. Hyperparameter tuning. Fine-tune hyperparameters such as learning rate, batch size, number of layers, and units in each layer to optimize the model's performance. 9. Evaluation. Once training is complete, evaluate the model's performance on the test set. Analyze metrics like MAE, RMSE, and potentially visualize predictions versus actual values. 10. Deployment and monitoring. Deploy the trained model in a production environment where it can make real-time or batch predictions. Monitor its performance over time and update it as needed. Here's a basic example code snippet using TensorFlow/Keras for a simple LSTM-based sales forecasting model. Python. Import NumPy as NP. Import TensorFlow as TF. From TensorFlow.Keras.Models import sequential. From TensorFlow.Keras.Layers import LSTM, dense. Hashtag load and pre-process your data. Hashtag. Hashtag define the LSTM model. Model equals sequential. Model.add, LSTM, 128, input underscore shape equals sequence underscore length, number underscore features, activation equals reload. Model.add, dense, 1. Hashtag compile the model. Model.compile, optimizer equals atom, loss equals mean underscore squared underscore error. Hashtag train the model. Model.fit, x underscore train, y underscore train, epochs equals epochs, batch underscore size equals batch underscore size, validation underscore data equals x underscore val, y underscore val. Hashtag evaluate the model. Loss equals model.evaluate, x underscore test, y underscore test. Hashtag make predictions. Predictions equals model.predict, x underscore test. Remember that this is just a basic example. In practice, you may need to fine-tune the model architecture, pre-process the data more extensively, and incorporate more advanced techniques to improve forecasting accuracy. Explain these terms. 1. RNN, recurrent neural network. A recurrent neural network is a type of neural network architecture designed to process sequences of data, where each data point in the sequence is dependent on the previous ones. RNNs have a recurrent connection that allows information to be passed from one step of the network to the next. However, basic RNNs suffer from the vanishing gradient problem, where the gradients become too small to effectively update the weights over long sequences. 2. LSTM, long short-term memory. LSTM is a specialized type of RNN designed to overcome the vanishing gradient problem. It introduces memory cells with gating mechanisms that control the flow of information, allowing the network to selectively remember or forget information over long sequences. LSTMs are particularly well suited for tasks that involve sequential or time series data, as they can capture long-range dependencies and patterns. 3. CNN, convolutional neural network. A convolutional neural network is a type of neural network architecture commonly used for image and spatial data analysis. CNNs excel at capturing local patterns in data by applying convolutional filters and pooling operations. These filters help extract features from input data while preserving spatial relationships. CNNs are widely used in tasks like image recognition, object detection, and image classification. 4. Transformers. Transformers are a revolutionary neural network architecture introduced in the Attention Is All You Need paper by Vaswani et al. Transformers have become the foundation of many state-of-the-art natural language processing, NLP, models. They use a mechanism called self-attention to process sequences of data in parallel, allowing them to capture relationships between all elements in the sequence. Transformers can handle tasks like language translation, text generation, and sentiment analysis. In the context of sales forecasting. For time series data where the order of data points matters, you might use LSTM to capture temporal dependencies and predict future sales based on historical patterns. If you're dealing with tabular data with multiple features, you might use a regular feed-forward neural network. For image data related to sales, example analyzing store images or product images, CNNs could be useful for feature extraction. Transformers are less commonly used for sales forecasting, as they are more tailored for handling sequences of data in the NLP domain. However, they could potentially be adapted to capture complex interactions in sales data. The choice of architecture depends on the nature of your data, the problem you're trying to solve, and the level of complexity required to capture the underlying patterns. How to create a basic diagram of a neural network using ASCII art. This will be a simplified representation, but it can help you visualize the layers and connections. Here's an example of a simple feed-forward neural network. Mathematica. Input layer, hidden layer, output layer. Backslash slash backslash slash. Slash backslash slash backslash. In this diagram, each O represents a neuron or node in the neural network. The lines connecting the neurons represent the connections, weights, between them. The layers are labeled, input layer, hidden layer, S, and output layer. You can use this as a starting point and modify it according to your specific architecture. For more complex networks with different layer types, LSTM, CNN, etc., the diagram will be more intricate. If you need more advanced and interactive visualizations, you might consider using tools like TensorBoard, for TensorFlow users, or external diagramming tools. Thank you.